Hello everybody, welcome to 2 plus 2. Today I'm going to be showing you how to convert this decimal number to the IEEE754 single precision format. Let's get right into it. The number in question is 129.4, and it's basically a positive decimal number. So what do we have to do first? Focus on this first part of the number, basically what comes before the decimal number, and divide it by 2. In this case we have 129 divided by 2. Let's take a look. 129, let's divide it by 2. That equals 64.5. Since the result of 129.2, so the result of the division is a decimal number, we have to forget about this 0.5 and write down 64 followed by a 1 right next to it. Then again, 64, this one, divided by 2, that is 32. Since 32 is a whole number, and it does not have points, so it's not a decimal number, write a 0 right next to it. Then again, 32 divided by 2, that is 16. So again, 16, 0, because 16 is not a decimal number. Then 16 divided by 2, that's 8. Then 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 equals 1. And then 1, watch out, 1 divided by 2, that's 0.5. So again, forget about the 0.5. Just write 0 with a 1 right next to it, because the result of this division, so 1 divided by 2, is a decimal number. We have to write this down, but watch out, be careful, from bottom to top, so from the bottom to the top. So 1, 0, 0, 0, 0, 0, 0, 1, just like so. Forget about this first line. Add a decimal point right here, right next to the 1, because it's going to be really useful later. Now what do we have to do? The second step is to focus on this, the 0.4 right here, and add a 0 right before it, and multiply it by 2. So 0.4 times 2, that is 0.8. Write it right here, then copy it right here. So transcribe it right here, and then again, times 2. 0.8 times 2, that is 1.6. Be careful now. We have to replace this 1 with a 0 and write it right here. So 0.6 times 2, that equals, hang on, 0.6 times 2, that's 1.2. So again, 1.2, I replace the 1 with a 0 and write it right here. So 0.2 times 2, that is 0.4. Then again, 0.4 times 2, that is 0.8, and so on. So again, 0.4 times 2, that is 0.8. Then 0.8 times 2, that is 1.6. Replace the 1 with a 0 and write it back here. 0.6 times 2, that is 1.2. Again, replace the 1 with a 0, so 0.2 times 2, that is 0.4. What do you notice here? It's actually a looping mechanism because, they loop, like that. It loops itself. So look, 0.8, 1.6, 1.2, 0.4, and then again, same thing. So we have to focus on this line, the first one, and forget about all this, the second line. It does not matter anymore. So we have to read it like this, from top to bottom. So 0, 1, 1, 0, 0, 1, 1, 0, and so on, because it repeats itself. So let's write it. 0, 1, 1, 0, 0, 1, 1, 0. It goes on and on and on and on. That's it. Now, the third step is moving this decimal point right here to this position between the first and the second digit. Let's do it. So move it to the left. 1, 2, 3, 4, 5, 6, 7. 7 times. So let's write it. 1 point. Then what comes after? Without this decimal point, because we moved it. 1, 1, 0. So we moved this 7 times. So right next to this, write times. That's the multiplication sign. 2 to the 7, because we moved this point to the left until it reached this position. So we moved it 7 times. There we go. That's the exponent. That's going to be really important later on. Now, what do we do next? The fourth step is to take our bias, which is 127 because we're dealing with the single precision format. If we were dealing with the double precision format, that would have been 1025. But since we are dealing with the single precision format, let's focus on this. This number, 127, that's the bias. It's actually a standard number. What do we have to do now? Let's focus on this and this. This is a positive number, so we need to add the exponent to the bias. 127, that's the bias, plus the exponent 7. If this was a negative number, let's say minus 129.4, we should have done it like this. Look, 127 minus 7. So we would have subtracted the exponent from the bias. But in this case, we're dealing with a positive number, so that's fine. 127 plus 7. So let's see, 127 plus 7, that is 134. Write it right here. And now let's do this same thing all over again. So draw a little arrow. 134 divided by 2. So again, 134 divided by 2, that is, 134 divided by 2, that is 67. Whole number, so it's not a decimal result, so 0 right next to it. 67 divided by 2, 33.5. So basically do the same thing again. 33 divided by 2, 16. Then 8, 4, 2, 1, and 0. 0, 0, 0, 0, 1. Bam. Really easy. And again, read it from the bottom to the top. Now, it's really important now to understand how the IEEE system works, the single precision system. So let's take a look. Like that. And then like that. These are going to be our bits. We have one single bit, that is the sign bit. It can either be 0 or 1 depending on this number. In this case, we're dealing with a positive number, so our sign bit is going to be 0. If it was a negative number, it would have been 1. But in this case, it's 0. So let's write our final answer right here. So 0 is going to be our sign bit. Then the exponential bits, precisely, that's going to be 8 bits dedicated to the exponent. So 8 plus 1 sign bit plus 23 bits that's going to be the mantissa. 23 bits. Now, let's focus on the second part of the answer and then the third one. The exponential bits are going to be these bits, just like that. So let's write it down for our final answer. 1, 2, 3, 4, 0, 0, 0, 0, 1, 1, 0. These are going to be our exponential bits, sign bit, and now the mantissa are going to be all these bits without the 1 point, so just forget about that. 1, 2, 3, 4, 5, 6. So 0 repeated 6 times, then 1, and then 0, 1, 1, 0. What do we do now? Add as many zeros as you can until you reach 23 bits. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Then again, 12, 13, 14, 15, and so on. So let's write our final answer together. I'm going to write it right here. So this is going to be our final answer. The conversion, call it whatever. We're going to write it down here. So our final answer is 0 as the sign bit. Then 1, 0, 0, 0, 0, 1, 1, 0. I'm going to divide it because it's actually 4 plus 4, 8 bits. And then the mantissa, which is 0 repeated 6 times. Then 1 and then 0, 1, 1, 0. This is our final answer. Now, as many zeros as you can until you reach 23, which is the number of bits for the mantissa. So let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. There we go. That is our final answer. Now, basically the meaning behind single precision format. So single precision, that means that we are going to be working. Actually, we already worked on 32 bits. So our final answer should contain 32 bits. Look, 1 plus 8 plus 23. Look at this. 1 plus 8 plus 23, that's actually 32. Look, 32 bits. So this is going to be our final answer, and it contains 32 bits. I'll see you guys in the next video. Thank you for watching. And in the next video, we're going to be talking about the double precision format. Bye!